The universe is full of mysteries that defy our understanding, and nowhere is this more evident than in the colossal Perseus Cluster. Picture a structure so immense it contains thousands of galaxies, each with billions of stars, all bound together by gravity in a cosmic dance spanning hundreds of millions of light years. This isn't just another cluster, it's one of the most massive objects we've ever discovered, a titan of the cosmos that holds secrets we're only beginning to unravel. And yet, despite its staggering scale, the Perseus Cluster is more than just a collection of celestial bodies. It's a hotspot for phenomena that challenge everything we think we know about space, time, and the very fabric of reality. From mysterious dark matter whispers to bizarre energy eruptions that shouldn't exist according to our current laws of physics, the Perseus Cluster is a treasure trove of cosmic anomalies. Some of these enigmas are so profound they've left scientists scratching their heads for decades. What could be causing these strange, unexplained signals? Are we looking at the fingerprints of an unknown force, or is there something even more extraordinary lurking in the depths of this cluster? The answers might rewrite our understanding of the universe itself. That's exactly what we're diving into today, 25 of the most baffling, awe-inspiring mysteries hidden within the Perseus Cluster. We'll explore everything from ghostly radio waves echoing through the void to galaxies that appear to move in ways physics says they shouldn't. Each one of these phenomena opens a door to a deeper question, a puzzle waiting to be solved. So get ready, because by the end of this journey, you won't just see the Perseus Cluster as a distant speck in the cosmos. You'll see it as a frontier of discovery, a place where the universe reveals its strangest, most captivating secrets. One of the most perplexing mysteries hiding within the Perseus Cluster isn't something we can see, it's something that isn't there at all. Dark matter, the invisible glue that holds galaxies together, seems to vanish in certain pockets of this colossal cluster, defying everything we thought we knew about how the universe works. Normally, dark matter outweighs visible matter by a staggering 5-to-1 ratio, weaving an unseen scaffold that shapes the cosmos. Yet, when astronomers mapped the gravitational influence across the Perseus Cluster, they stumbled upon regions where this cosmic scaffolding simply disappears. It's like finding a skyscraper floating in midair with no foundation. It shouldn't be possible. So what's going on? One leading theory suggests these dark matter voids might be the aftermath of cosmic collisions. When galaxies ram into one another, their visible stars and gas get tangled up, but the dark matter, being immune to friction, could slip right through, leaving behind ghostly gaps. Another, even wilder idea is that dark matter isn't missing at all, but our understanding of gravity itself is flawed. Maybe Einstein's theory needs an update, and what we're seeing is a sign of gravity behaving differently on cosmic scales. But here's where it gets even stranger. Some of these dark matter-deficient zones align with bizarre, high-energy phenomena, like unexplained X-ray flares or ripples in the cluster's superheated gas. Could these be clues pointing to an unknown interaction between dark matter and the extreme environments of the cluster? Or is there something entirely new at play, a force or particle we haven't even imagined yet? Every time we think we've got dark matter figured out, the Perseus Cluster throws another curveball. These eerie voids aren't just academic curiosities, they're cosmic riddles that could rewrite the rules of physics. And until we solve them, a fundamental piece of the universe's blueprint remains missing. Deep within the heart of the Perseus Cluster, something extraordinary is happening, a pair of colossal radio bubbles, each stretching tens of thousands of light years across, billowing outward like cosmic smoke rings. These aren't just any structures, they're among the largest and most energetic phenomena ever observed, pumping out radio waves with an intensity that defies conventional explanation. Astronomers first spotted these gargantuan bubbles using radio telescopes, their ghostly glow standing out against the cluster's swirling sea of hot gas and galaxies. But what could possibly create such massive, symmetrical structures in one of the most violent environments in the universe? The leading suspect lies at the very center of the cluster, a supermassive black hole billions of times heavier than our Sun. When black holes feed, they don't just swallow matter quietly. They erupt in titanic outbursts of energy, spewing jets of particles at nearly the speed of light. These jets, powered by the black hole's insane gravitational pull, could inflate the radio bubbles like cosmic balloons over millions of years. But there's a problem. The energy required to create bubbles this big is off the charts, far beyond what even the most active black holes should theoretically produce. It's like trying to power a city with a single A battery. The numbers just don't add up. Even stranger, these bubbles aren't static. They pulse and ripple as if alive, with shockwaves traveling through them at speeds that challenge our understanding of how energy dissipates in space. Some researchers speculate that the cluster's superheated gas might be interacting with the bubbles in unexpected ways, amplifying their size and longevity. Others wonder if we're witnessing a new kind of astrophysical phenomenon, one where dark matter or even unknown quantum effects play a role. What's clear is that these radio bubbles are more than just a cosmic curiosity. They're a window into the extreme physics governing the universe's most powerful engines. And until we crack their secrets, they'll remain one of the Perseus Cluster's most tantalizing mysteries, whispering hints of forces we've yet to comprehend. Imagine a cosmic storm so powerful it defies the laws of physics, where waves of gas, colder than the space around them, surge through a superheated inferno at speeds faster than sound. This isn't science fiction, it's the bizarre reality of the Perseus Cluster's cold fronts. These vast, whip-like structures of chilled gas, some stretching over 2 million light-years, slash through the cluster's scorching atmosphere at thousands of miles per second, leaving scientists baffled. How can something colder than its environment not only survive but race through one of the most extreme places in the universe without instantly evaporating? At first glance, this shouldn't be possible. The Perseus Cluster is filled with gas so hot it glows in X-rays, reaching temperatures of tens of millions of degrees. Normally, if you introduced a pocket of cooler material here, it would vanish in seconds, vaporized by the overwhelming heat. Yet these cold fronts persist for hundreds of millions of years, carving precise, razor-sharp edges through the chaos. It's like watching an ice cube glide unharmed through molten lava, a phenomenon that flips our understanding of thermodynamics on its head. The mystery deepens when we examine their speed. These cold fronts don't creep, they tear through space at supersonic velocities, creating shock waves that ripple across the cluster. Such motion should generate enough turbulence to shred the cold gas into oblivion, yet somehow the structures remain eerily intact. Some researchers propose magnetic fields might be acting as invisible shields, wrapping around the cold gas like a protective cocoon. Others suggest the fronts are cosmic relics, leftover debris from ancient collisions where smaller galaxy clusters smashed into Perseus, dragging their colder atmospheres along like interstellar contrails. But the most mind-bending twist, these cold fronts might be hiding clues about the cluster's turbulent past. Their intricate shapes, some spiral, some jagged, mirror the violence of the Perseus Cluster's formation, like fingerprints of long-forgotten cosmic battles. And here's the kicker, some simulations show these fronts could actually be heating the surrounding gas as they plow through it, sparking a feedback loop that keeps the cluster's atmosphere simmering. That means what we're seeing isn't just a quirk of nature. It's a dynamic engine quietly shaping the evolution of one of the universe's most massive structures. So why does this matter? Because if we can unravel how these cold fronts defy destruction, we might unlock secrets about how all galaxy clusters evolve, and how the universe itself governs energy, chaos, and order on the grandest scales. For now, though, they remain one of the Perseus Cluster's most defiant puzzles, challenging us to rethink what's possible in the cosmic furnace. Scattered throughout the Perseus Cluster, like cosmic breadcrumbs leading to an unsolved riddle, are mysterious bursts of X-ray energy with no obvious source. These aren't just faint blips, they're powerful emissions, some bright enough to outshine entire galaxies. Yet when astronomers point optical telescopes at their locations, they find nothing, no stars, no black holes, no visible objects that could explain the staggering amounts of energy being released. It's as if the universe is flicking invisible light switches, and we're left scrambling to understand what's flipping them on. The leading theory points to hidden black holes, monsters lurking in the darkness, too faint or too shrouded in dust to be seen directly. Supermassive black holes at the hearts of galaxies often emit X-rays as they devour matter, but these unexplained sources are different. They don't match the typical signatures of feeding black holes, lacking the telltale jets or accretion disks we'd expect. Some might be intermediate mass black holes, an elusive class that's heavier than star-sized black holes but lighter than the supermassive beasts at galactic centers. These cosmic middleweights could be drifting undetected, occasionally flaring up when they snatch a passing star or gas cloud. But there's a wilder possibility. What if these X-ray sources aren't black holes at all? Some astrophysicists speculate they could be signs of dark matter, the universe's most enigmatic substance behaving in ways we've never witnessed. Certain theoretical models suggest dark matter particles could collide and annihilate in dense regions like the Perseus Cluster, releasing bursts of energy in the form of X-rays. If true, these mysterious flashes might be our first direct glimpse into the hidden interactions shaping the cosmos. The plot thickens when you examine their distribution. These X-ray sources aren't randomly scattered, they often cluster near the edges of the Perseus Cluster's massive radio bubbles or along the paths of its turbulent cold fronts. Could they be triggered by the extreme conditions there? Imagine shockwaves from ancient galaxy collisions rippling through the cluster, compressing dark matter or igniting dormant black holes like cosmic dominoes. Or perhaps we're seeing the aftermath of stars torn apart by tidal forces, their debris glowing briefly in X-rays before vanishing into the void. Here's the kicker: some of these sources flicker unpredictably, flaring and fading over timescales that defy conventional explanations. A black hole feasting on gas should brighten steadily, not pulse like a strobe light. This erratic behavior has led to even more exotic hypotheses, like quark stars, hypothetical ultra-dense objects made of subatomic particles beyond neutrons, or defects in spacetime itself releasing pent-up energy. Every time we get closer to solving this puzzle, the Perseus Cluster throws another curveball. These phantom X-ray sources aren't just celestial oddities, they're potential keys to unlocking new physics. Whether they are hiding unseen black holes, exposing dark matter's secrets, or pointing to something entirely unexpected, one thing's clear: the universe is still playing its cards close to the chest. And until we crack this code, these mysterious beacons will keep challenging our understanding of the cosmos' most fundamental rules. The Perseus Cluster holds galaxies of every shape and size, but none are quite as enigmatic as its ultra-diffuse galaxies, ghostly, sprawling islands of stars so faint they nearly vanish against the blackness of space. These cosmic specters stretch tens of thousands of light-years across, rivaling the Milky Way in size, yet contain only a fraction of its stars, making them some of the most ethereal objects ever discovered. Picture a galaxy where the night sky would be almost pitch black, with stars spaced so far apart that neighboring suns might be hundreds of light-years away. How can something so vast remain so empty, and why does the Perseus Cluster seem to harbor so many of these shadowy giants? The mystery begins with their origins. Most galaxies form through the steady collapse of gas clouds, which ignite stars in dense, brilliant spirals or ellipticals. But ultra-diffuse galaxies defy this logic. they're cosmic underachievers, failing to convert their gas into stars despite having ample raw material. One theory suggests they were born in quieter cosmic backwaters, where the sparse gas never clumped tightly enough to spark widespread star formation. Another idea paints a more violent picture. These galaxies might be the mangled remnants of smaller systems shredded by the Perseus Cluster's immense gravity, their stars scattered like dust in a hurricane. Yet the plot thickens when you consider their survival. The Perseus Cluster is a brutal environment filled with searing plasma and gravitational tides strong enough to rip galaxies apart. Normally, delicate ultra-diffuse galaxies shouldn't last long here, but somehow they persist. Some could be protected by vast halos of dark matter, acting like invisible armor against the cluster's chaos. Others might be cosmic zombies already stripped of their gas by past encounters, leaving behind only skeletal frameworks of ancient stars, but the real head-scratcher is their strange distribution. These ghostly galaxies aren't randomly scattered, they often lurk near the cluster's edges, as if pushed there by some unseen force. Even more puzzling, a few have been caught with unexpected pockets of fresh star formation, defying their reputation as cosmic dead zones. Could intermittent brushes with the cluster's gas clouds reignite their starbirth engines, or are we seeing the influence of hidden phenomena like rogue dark matter clumps or interstellar magnetic fields? Ultra-diffuse galaxies are more than just celestial curiosities, they're stress tests for our theories of galaxy evolution. Each one forces us to ask how much of a galaxy's fate is written in its genes, and how much is shaped by the ruthless environment of a place like the Perseus Cluster. Until we solve this riddle, these phantom galaxies will keep challenging our assumptions, reminding us that even in the brightest corners of the universe, darkness still has secrets to spill. Threading through the Perseus Cluster like luminous cobwebs, vast filaments of superheated gas weave an intricate tapestry across the cosmos. These aren't random tendrils, they're colossal structures, some spanning over 50,000 light-years, glowing faintly in X-rays as they snake through the cluster's turbulent atmosphere. At first glance, they might resemble the aftermath of an explosion, but their precise, almost artistic arrangement hints at something far more deliberate. How do these delicate threads survive in one of the most violent environments in the universe, and what cosmic loom could have woven them into existence? The answer might lie in the invisible forces shaping the cluster. Magnetic fields, imperceptible to our eyes but powerful enough to guide entire galaxies, could be sculpting these filaments into their eerie, elongated forms. Picture the cluster's superheated plasma as a turbulent ocean, with magnetic field lines acting like submerged ropes, channeling the gas into orderly streams amid the chaos. Simulations show that when these magnetic forces interact with the cluster's swirling currents, they can stretch and twist the gas into the very filaments we observe, like taffy being pulled into thin strands by an unseen hand. But there's another, more explosive possibility. These filaments could be scars from ancient cosmic collisions. When smaller galaxy clusters plow into the Perseus Cluster, their gas doesn't just mix smoothly, it's shredded and stretched into ribbons by the immense gravitational forces at play. Think of it as throwing a handful of paint into a whirlpool. The colors don't blend evenly but get drawn out into streaks and swirls. Some filaments might even trace the orbits of long-vanished galaxies, their gaseous remains smeared across the void like fingerprints on a window. The real enigma, though, is their endurance. Gas this hot should dissipate quickly, its particles scattering like smoke in the wind. Yet these filaments persist for hundreds of millions of years, defying the cluster's violent churn. One clue comes from their temperature. Some filaments are slightly cooler than their surroundings, suggesting they might be wrapped in protective magnetic sheaths that insulate them from the surrounding inferno. Others could be continuously replenished by new material, like rivers fed by hidden underground springs, with gas funneled into them by the cluster's complex dynamics. What's most astonishing is their role in the cluster's ecosystem. These filaments aren't just passive relics, they're cosmic highways, channeling gas and energy across vast distances. Some appear to funnel material toward the cluster's central black hole, feeding its monstrous appetite. Others might act as shock absorbers, dissipating energy from collisions and preventing the cluster's atmosphere from overheating. And here's the kicker: a few filaments seem to glow with unusual intensity, as if they're conducting electrical currents on a galactic scale, a phenomenon that could hint at entirely new forms of astrophysical energy transfer. Every time we study these filaments, they reveal another layer of complexity. Whether they're magnetic masterpieces, collision remnants, or something even more exotic, one thing's clear: the Perseus Cluster isn't just a random scattering of galaxies. It's a carefully structured universe in miniature, with these filaments as its hidden blueprints, silent architects of order in the cosmic storm. And until we decode their full story, they'll remain one of the most elegant mysteries in the heavens. At the heart of the Perseus Cluster, nestled within the unassuming galaxy NGC 1277, lurks a cosmic anomaly so extreme it upends everything we thought we knew about black holes and their hosts. This isn't just any supermassive black hole. It's a behemoth weighing in at a staggering 17 billion times the mass of our Sun, a figure so mind-boggling it dwarfs the black hole at the center of our own Milky Way by over 4,000 times. But here's the catch: NGC 1277 itself is a modest, compact galaxy, barely a tenth the size of the Milky Way. According to every established rule of astrophysics, a galaxy this small couldn't host a black hole of this magnitude. It's like finding a skyscraper perched on a rowboat. The proportions defy logic. So how did this overgrown monster come to exist? The leading theory suggests it's a relic from the universe's chaotic infancy, a primordial black hole that formed when the cosmos was young and dense. In those early days, massive clouds of gas could have collapsed directly into black holes without first forming stars, birthing titans like the one in NGC 1277. Over billions of years, while other galaxies grew around their central black holes through mergers and star formation, NGC 1277 might have remained frozen in time, its growth stunted by the harsh environment of the Perseus Cluster. But this explanation raises new questions. Why didn't this black hole accumulate more stars and gas around it? And why haven't we found more of these ancient giants lurking in other small galaxies? The implications ripple far beyond NGC 1277. For decades, astronomers have relied on scaling relations, mathematical rules linking a galaxy's size to its central black hole's mass, to predict how these cosmic engines evolve. But NGC 1277 black hole breaks these rules spectacularly, suggesting our models might be missing a crucial piece of the puzzle. Some researchers argue that black holes could grow in fits and starts, with periods of explosive feeding followed by long droughts, creating outliers like this one. Others propose that the extreme gravitational tides in the Perseus Cluster might have stripped away NGC 1277 outer stars, leaving only its overt black hole exposed like a cosmic carcass. The most tantalizing possibility: this black hole might not be alone. If NGC 1277 anomaly isn't a fluke but a sign of a larger population of overmassive black holes, it could mean our universe's history is far stranger than we imagined. Picture a hidden class of black holes, relics from a bygone era, lurking unnoticed in plain sight, rewriting the story of how galaxies and their dark hearts co-evolve. Until we solve this mystery, NGC 1277 black hole stands as a glaring exception, a cosmic rebel forcing us to rethink the rules of the universe. And in its defiance, it offers us something rare, a chance to glimpse the untold chapters of cosmic history. The Perseus Cluster isn't just broadcasting its mysteries in visible light or X-rays, it's also sending us ghostly signals in the form of neutrinos, the universe's most elusive particles. These tiny, nearly massless phantoms zip through space at near light speed, passing through planets and stars as if they weren't even there. Trillions shoot through your body every second without a trace. But when scientists trained neutrino detectors toward the Perseus Cluster, they caught something odd. A surge of high-energy neutrinos, far more than expected, pouring in from its direction. Where are they coming from? The answer might rewrite the rules of particle physics. Neutrinos this energetic don't just appear out of nowhere. They're the product of cosmic violence, born in the aftermath of some of the universe's most extreme events. Normally, we'd blame supermassive black holes or colliding galaxies, the usual suspects for high-energy particle production. But here's the twist: the Perseus Cluster's neutrino excess doesn't match up with any known sources within it. No visible black hole outbursts or gamma-ray flares coincide with the detections. It's as if the cluster is hiding an invisible particle accelerator, one that flings neutrinos at us without leaving any other trace. This has led scientists down two thrilling paths. The first involves dark matter, the universe's missing scaffold. Some theories suggest dark matter particles could collide and annihilate in dense regions like the Perseus Cluster, producing bursts of neutrinos as a byproduct. If true, this excess might be our first direct clue to dark matter's identity, a fingerprint left at the scene of an invisible crime. The other path points to something even stranger: hidden cosmic accelerators. Imagine vast magnetic fields, twisted by the cluster's turbulent plasma, acting like unseen slingshots to launch particles to unimaginable speeds. These could be natural versions of the Large Hadron Collider, operating on scales we've never witnessed before. But the plot thickens. These neutrinos arrive with a peculiar energy signature too powerful to come from ordinary particle collisions, yet not quite matching predictions for dark matter either. Some researchers speculate we're seeing a blend of both: dark matter decay sparking chain reactions in the cluster's gas, or even an entirely new class of particle interactions. Others wonder if the Perseus Cluster's extreme environment is amplifying neutrino production in ways our models can't yet predict. One thing's certain: this ghostly excess isn't just a fluke. Multiple detectors have now spotted similar patterns, adding weight to the mystery. Whether it's dark matter's whisper or the cry of hidden cosmic machinery, these neutrinos are sending us a message. And decoding it could crack open one of the universe's best-kept secrets. Among the many enigmas of the Perseus Cluster, few are as unsettling as the case of the vanishing galaxies. Astronomers have watched as seemingly normal galaxy spirals brimming with stars or ellipticals glowing steadily suddenly dim, distort, or disappear entirely from observations over surprisingly short cosmic timescales. It's as if the cluster itself is a cosmic magician, making entire galaxies vanish without a trace. But this isn't illusion, it's a real astronomical puzzle with consequences that ripple across our understanding of how galaxies live and die in the universe's most crowded neighborhoods. So what's causing these disappearances? One leading culprit is tidal disruption, a brutal process where the cluster's immense gravity stretches and shreds galaxies like taffy. Picture a galaxy wandering too close to the cluster's crowded core. The gravitational pull from neighboring galaxies and dark matter yanks stars from its edges, unraveling it into long, faint streams that eventually fade into the void. Some galaxies might not vanish completely but transform into unrecognizable ghosts, their stars scattered so thinly they become nearly invisible against the blackness of space. This isn't just theory, we've caught this violence in action. Hubble images reveal galaxies in the Perseus Cluster with tails of stars stretching hundreds of thousands of light years, like cosmic breadcrumbs marking their slow dissolution. But tidal forces aren't the only explanation. Another shocking possibility is quenching, a sudden shutdown of star formation that can turn vibrant galaxies into cosmic mummies. In the Perseus Cluster, galaxies often plunge through clouds of superheated gas so dense it acts like an interstellar wind, stripping away their star-forming fuel in a process called ram pressure stripping. Imagine a candle flame hit by a hurricane. The galaxy's gas, essential for creating new stars, gets blown away in an instant. Without fresh stars to keep them luminous, these galaxies dim rapidly, their remaining stars aging into a dim, red glow that's easy to overlook in surveys. Here's where it gets even stranger. Some galaxies seem to disappear not because they're being torn apart or starved, but because they're being hidden. The Perseus Cluster is filled with dense clouds of dust and plasma that could, over time, envelop entire galaxies, obscuring them from our telescopes. It's like throwing a blanket over a lamp. The light's still there, but we can't see it. Infrared observations have hinted at galaxies lurking behind these veils, their light redshifted and dimmed by the intervening material. Could there be a whole population of shadow galaxies hiding in plain sight, waiting to be discovered? The implications are profound. If galaxies can vanish or transform this quickly, our census of the cosmos might be far less complete than we thought. Worse, we might be missing key stages of galactic evolution, leaving gaps in our understanding of how clusters shape their inhabitants. Some researchers even speculate that these disappearing acts could explain why we find fewer small galaxies in clusters than predicted. Perhaps many have already been erased, their stars dissolved into the cluster's diffuse halo. Yet for every galaxy that vanishes, the Perseus Cluster seems to create new mysteries in its place. Some fading galaxies leave behind ultra-compact remnants, dense knots of stars that stubbornly resist disruption. Others trigger bursts of star formation in their death throes, as if the pressure of their destruction ignites one final blaze of stellar birth. And then there are the rogue stars cast adrift from their parent galaxies, now wandering the cluster alone, invisible except as a faint collective glow. What makes these disappearances so fascinating isn't just the violence behind them, but what they reveal about the dynamic, ever-changing nature of galaxy clusters. The Perseus Cluster isn't a static museum of galaxies, it's a cosmic battlefield where gravitational tides, scorching plasma, and dark matter conspire to rewrite galactic destinies. And with every galaxy that vanishes, we're reminded how much of the universe's drama unfolds unseen in the shadows between the stars. Among the countless mysteries of the cosmos, few are as perplexing as the dark flow, a phenomenon where entire galaxy clusters, including Perseus, appear to be pulled towards something beyond the edge of our observable universe. This isn't just random motion, it's a coordinated drift, as if hidden hands are tugging at the fabric of spacetime itself. Imagine setting a dozen boats adrift on a calm lake, only to watch them all move steadily in the same direction, defying the wind and currents. That's the eerie consistency of the dark flow, and it raises a question that unsettles even seasoned cosmologists. What colossal force could possibly be governing the motion of structures as vast as the Perseus Cluster? The discovery came from studying the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light revealed something astonishing. Galaxy clusters weren't just moving outward with the universe's expansion. They showed a faint but measurable preference for one direction, streaming toward a patch of sky near the constellations Centaurus and Hydra at speeds exceeding 2 million miles per hour. At first, scientists suspected errors in the data, but repeated observations confirmed it. Something out there, something we can't see, is exerting a gravitational pull powerful enough to influence clusters hundreds of millions of light years away. Theories attempting to explain this anomaly range from the audacious to the revolutionary. One possibility is that the dark flow traces its origins to the very early universe, when regions beyond our cosmic horizon were still connected to us. Inflation, the rapid expansion of spacetime after the Big Bang, could have stretched these regions beyond visibility, but their gravitational imprint might linger, tugging at the matter within our observable bubble like a distant magnet. Another, even more radical idea suggests we're seeing the influence of another universe entirely. In certain multiverse models, neighboring universes could brush against our own, their gravity leaking through the boundaries of space-time and nudging galaxies toward them. Yet skeptics argue there might be a simpler explanation. Could the dark flow be an illusion, a statistical fluke amplified by the way we map cosmic motions? Or might it stem from something inside our universe, an immense supercluster so vast we haven't mapped it yet? The Shapley Attractor, a known concentration of galaxies about 650 million light-years away, exerts a noticeable pull, but its gravity alone can't account for the dark flow's scale. Some researchers propose an even larger structure lurking behind it, a cosmic titan hidden by dust and distance. The stakes couldn't be higher. If the dark flow is real, it implies that our universe is far less uniform than we thought, that beyond the visible cosmos lie structures so enormous they redefine our understanding of reality. It challenges the cosmological principle, the bedrock assumption that the universe looks roughly the same in all directions, and if the culprit is another universe, then the dark flow isn't just an anomaly, it's our first glimpse into the infinite. For now, the Perseus Cluster and its neighboring clusters continue their mysterious journey, swept along by forces we can't yet name. Whether this motion leads us to hidden dimensions, unseen giants, or flaws in our fundamental theories, one thing's certain: the dark flow is a compass pointing toward the next great frontier of cosmology. And wherever it takes us, the destination promises to rewrite the story of the universe. The Perseus Cluster isn't just a spectacle of swirling galaxies and searing gas. It's also humming with an eerie radio whisper, a vast and diffuse halo of emission that envelops the entire structure like an invisible cosmic shroud. Unlike the sharp, focused radio signals from active galaxies or black hole jets, this halo is faint and sprawling, stretching across millions of light-years with no obvious source. It's the astrophysical equivalent of hearing a choir's distant murmur without ever spotting the singers. What could possibly produce such a uniform, all-encompassing radio glow in one of the universe's most turbulent environments? The answer might lie in the chaos of the cluster itself. When galaxies collide or gas slams together at thousands of miles per second, they don't just create fireworks, they generate shockwaves that ripple through the cluster's atmosphere like sonic booms. These shocks could be accelerating electrons to near light speeds, sending them spiraling around magnetic fields and releasing radio waves as they go. Think of it as a natural particle accelerator on a galactic scale, where the violence of the Perseus Cluster's mergers acts like a cosmic blender, churning out energetic particles that paint the sky with radio light. But there's a catch: the halo's sheer size and smoothness defy simple explanations. If mergers alone were responsible, we'd expect patchy, uneven emission, reflecting localized bursts of violence. Instead, the radio halo is remarkably uniform, suggesting something else, perhaps a reservoir of ancient particles, stirred up by the cluster's ongoing turbulence and kept alive by its magnetic fields. Some researchers even speculate that dark matter could play a role, with hypothetical particles decaying or interacting to produce a faint radio hum. The plot thickens when you compare Perseus to other clusters. Some of the most massive galaxy clusters sport similar halos, but with puzzling variations in brightness and structure. Why does Perseus' halo appear smoother than most? Could its unique merger history, a slower, more drawn-out series of collisions, have created conditions for this peculiar radio blanket? Or is there an unseen mechanism at work, something that connects the halo's glow to the cluster's other mysteries, like its cold fronts or phantom X-ray sources? What makes this enigma so compelling is its potential to reveal hidden physics. The halo's electrons must come from somewhere, and their distribution hints at how energy flows through the cluster, how cosmic violence gets recycled into subtle, pervasive light. If we can decode this process, we might unlock secrets about particle acceleration in extreme environments, or even find new ways to map the invisible magnetic fields weaving through the cosmos. For now, though, the radio halo remains a quiet enigma, a whisper from the Perseus Cluster that we're only just learning to hear. Buried within the Perseus Cluster's sea of galaxies lies a peculiar enigma. Certain galaxies appear to be playing tricks with their light. Their redshift measurements, the telltale stretch of light waves we use to gauge cosmic distances, don't line up with expectations. Some galaxies show redshifts that place them much farther away than the cluster itself, while others seem suspiciously close, as if they're floating in front of a cosmic backdrop they clearly belong to. It's the astronomical equivalent of spotting a family photo where some members appear decades older or younger than they should be. What's throwing off these cosmic yardsticks, and could it hint at something deeper than mere measurement errors? First, let's untangle how redshift normally works. When light travels across the expanding universe, its wavelengths stretch like taffy, shifting toward the red end of the spectrum. The farther the light journeys, the more extreme this redshift becomes. It's why we can estimate a galaxy's distance by how red its light appears. But in the Perseus Cluster, this reliable rule crumbles for certain galaxies. Their redshifts suggest motions that defy the cluster's gravitational pull, like leaves fluttering upward in a downward rushing river. One possible explanation lies in peculiar velocities, local movements superimposed on cosmic expansion. Imagine two cars on a highway, one speeding ahead, the other slamming its brakes. Even as the road itself stretches akin to universal expansion, their individual motions distort the big picture. In Perseus, galaxies might be hurtling toward or away from us at unusual speeds due to the cluster's intense gravity, warping their redshift signals. Collisions between galaxies could slingshot them at thousands of miles per second, muddying the waters. But instrumental errors can't be ruled out. Measuring redshift involves dissecting faint light across vast distances, and cosmic dust or instrumental noise might skew results. Yet when multiple telescopes from Hubble to ground-based observatories keep recording these inconsistencies, the glitch theory starts to wobble. That's when things get interesting. A fringe but tantalizing idea suggests these anomalies might reveal flaws in our understanding of redshift itself. Could light behave differently in extreme environments like the Perseus Cluster? Some theorists propose that photons, the particles of light, might interact with mysterious quantum fields or even dark matter in ways that subtly alter their wavelengths during their journey. Others wonder if the fabric of spacetime within massive clusters warps light unpredictably, like funhouse mirrors bending reflections, the most radical possibility. These redshift mismatches could be signatures of tired light, a long-debated alternative to cosmic expansion. In this controversial model, light loses energy over vast distances not because space stretches, but due to some unknown interaction with the void. While most astrophysicists dismiss it, the Perseus Cluster's stubborn outliers keep the idea on life support. What makes these inconsistencies more than just cosmic bookkeeping errors is their pattern. They're not randomly scattered. Many cluster near the Perseus Cluster's turbulent core or along the paths of its cold fronts. Could shockwaves from ancient mergers or swirling magnetic fields be tweaking the light we see? Or is there a hidden population of high-speed, rogue galaxies ejected from cosmic crashes, skewing the averages? Every contradictory redshift is a breadcrumb leading to deeper questions. Are we seeing the limits of our tools, the chaos of cluster dynamics, or something fundamentally new? Until we solve this, the Perseus Cluster's conflicting light signatures will remain a quiet rebellion against the tidy rules of cosmology, a reminder that even our most trusted cosmic yardsticks might need recalibrating. Nestled within the ancient sprawl of the Perseus Cluster, astronomers have stumbled upon a cosmic contradiction: stars that simply shouldn't exist. These stellar youngsters blaze with the vigor of recent birth, their blue-white light standing out sharply against the redder glow of their elderly neighbors. The problem: the Perseus Cluster is old. Like really old, a relic of the early universe where most star formation should have fizzled out billions of years ago. So why are these infant stars flashing energetic winks at us from a graveyard of aging galaxies? It's the equivalent of finding a toddler at a retirement home, and astrophysicists are scrambling to explain their presence. One compelling theory points to galactic theft. In the dense urban sprawl of the cluster, galaxies frequently brush past one another, their gravitational pull snatching gas from their neighbors like cosmic pickpockets. A gas-rich spiral galaxy venturing too close to the cluster's core might have its star-forming fuel ripped away, only for that stolen material to later collapse into new stars within a different galaxy. Picture a cosmic relay race where gas passes from one galaxy to another, igniting fresh starbursts eons after the cluster's prime era of star formation. This could explain why some galaxies in the Perseus Cluster sport suspiciously young stellar populations. They're not actually young, just late bloomers. They're star-making materials delayed by billions of years of interstellar tug-of-war. But there's a twist. Some of these youthful stars aren't neatly tucked inside galaxies at all. They're found adrift in the cluster's intracluster medium, the vast and supposedly barren space between galaxies. How did they get there? One possibility is that they were ejected during galactic collisions, hurled into the void by gravitational slingshots. Another, more provocative idea suggests these stars formed in place from pockets of gas too diffuse to create full galaxies, but dense enough to spark sporadic stellar birth. It's like finding wildflowers sprouting from cracks in a concrete highway, proof that nature finds a way even in the most inhospitable environments. The plot thickens when you consider the composition of these stars. Many are unusually rich in heavy elements, the kind forged in supernova and scattered by stellar winds. This hints at a dramatic backstory. The gas they formed from might have been recycled through multiple generations of stars, enriched by explosions before settling into quiet nurseries. It's cosmic recycling on an epic scale, where the ashes of dead stars become the building blocks of new ones, long after the rest of the cluster has moved on. Yet the most tantalizing clue lies in their distribution. These youthful stars often cluster near the Perseus Cluster's colossal radio bubbles or along the arcs of its cold fronts, as if the same shocks and turbulence that sculpt the cluster's large-scale structure are also triggering localized star formation. It's a feedback loop of cosmic violence. Collisions and outbursts churn the gas, compressing it just enough to ignite new stars, which in turn explode and enrich the next wave of star birth. What makes these too young stars more than just a curiosity is what they reveal about galactic resilience. Even in a place as hostile as the Perseus Cluster, where gravitational tides rip galaxies apart and superheated gas scours away star-forming fuel, the universe still finds ways to create. Whether through delayed star formation, stolen gas, or improbable intracluster births, these stellar interlopers challenge our assumptions about how and where stars can emerge. And until we understand their full story, they'll keep reminding us that even in the oldest corners of the cosmos, the lights are still turning on. Hidden within the heart of the Perseus Cluster, a silent storm of gamma rays pulses with unexplained intensity. These aren't the ordinary high-energy photons we'd expect from supermassive black holes or colliding stars. This is a diffuse, persistent glow bathing the cluster's core, defying straightforward explanation. Gamma rays are the universe's brightest flashbulbs, typically produced in the most violent cosmic events, yet here they're lingering like an afterthought, as if the cluster itself is exhaling light. The mystery: we can't pinpoint what's breathing out this energy. One tantalizing possibility ties back to dark matter, the universe's most elusive architect. Certain theoretical models suggest dark matter particles could annihilate when they collide, converting their mass into pure energy, including gamma rays. If true, the Perseus Cluster's glow might be the first visible smoke from this invisible fire. Picture trillions of dark matter particles swirling in the cluster's gravitational well, occasionally crashing together and vanishing in bursts of light. The sheer density of dark matter here could make it a prime hunting ground for such signals. But there's a hitch. The gamma-ray excess doesn't perfectly match predictions for dark matter annihilation. The energy distribution is slightly off, like a fingerprint that's almost recognizable but not quite. Then there's the other contender, unresolved point sources. The Perseus Cluster is crowded with astrophysical powerhouses, supermassive black holes, neutron stars, and remnants of dead galaxies, any of which could be spewing gamma rays. But when astronomers comb through the data, they find no single culprit bright enough to explain the glow. Instead, it's as if thousands of faint, overlapping sources are contributing, like a chorus of whispers adding up to a shout. Could there be a hidden population of pulsars, too dim to spot individually but collectively flooding the cluster with gamma rays? Or perhaps microquasars, miniature versions of active galactic nuclei lurking undetected? The plot thickens when you consider the glow's distribution. It isn't uniform, it's concentrated in the cluster's inner regions, yet avoids perfect alignment with known structures like the central black hole or radio bubbles. This spatial oddity suggests something more nuanced at play, maybe interactions between cosmic rays and the cluster's magnetic fields, or even decaying particles from an exotic physics process we've yet to discover. What makes this enigma so thrilling is its potential to rewrite multiple cosmic rulebooks. If dark matter is indeed annihilating here, we're glimpsing a fundamental property of the universe's hidden scaffolding. If it's unresolved sources, we're staring at an entire undocumented class of celestial objects. Either way, the Perseus Cluster's gamma-ray glow isn't just a curiosity, it's a beacon, illuminating the edge of our understanding and daring us to look closer. The Perseus Cluster holds another cosmic card up its sleeve: gravitational lensing effects that don't add up. Normally, when light from distant galaxies passes through the cluster's immense gravity, it bends like a straw in a glass of water, creating stretched and distorted images called Einstein rings or arcs. These celestial mirages let astronomers weigh the cluster indirectly, calculating how much mass must be present to warp spacetime so drastically. But here's the catch: the lensing distortions in Perseus are stronger than they should be based on visible matter alone. Even accounting for the cluster's superheated gas and dark matter halo, there's a glaring mismatch. Some lenses appear far more powerful than our best models predict. It's as if the universe is tightening an invisible wrench on spacetime, and we can't see the hand turning it. This anomaly forces us to confront two possibilities, each with profound implications. First, our maps of dark matter in the Perseus Cluster might be incomplete. Dark matter isn't spread evenly, it clumps in filaments and halos, and if we've underestimated its density in certain regions, that could explain the extra lensing. Imagine pouring syrup onto a pancake and assuming it's evenly distributed, only to find hidden pockets where it's pooled thicker. Some researchers suggest the cluster could harbor unseen dark matter substructures, invisible islands of mass amplifying the bending of light in localized spots. The second possibility is far more radical. Our understanding of gravity itself might need an overhaul. Modified Newtonian dynamics, or MND, proposes tweaks to gravity's equations to explain cosmic motions without invoking dark matter. While MND has had mixed success elsewhere, the Perseus Cluster's lensing oddities give it renewed relevance. Think of it as recalibrating a scale. If gravity behaves slightly differently in extreme environments like galaxy clusters, no dark matter would be needed to account for the extra lensing. Yet even MND struggles to fully explain these observations, leaving room for even wilder ideas, like dark matter particles interacting with each other through unknown forces. What makes this puzzle particularly tantalizing is the lensing patterns themselves. Some distorted background galaxies appear brighter or more warped than simulations predict, hinting at small-scale dark matter clumps we can't directly detect. Others show asymmetries that suggest the cluster's gravity isn't perfectly smooth, as if immense, unseen structures are tugging at the fabric of spacetime from the shadows. Even stranger, a few lensed images seem to flicker over time, as though the lensing mass is shifting, though nothing visible moves. One of the most head-scratching cases involves a distant galaxy lensed into multiple images around the Perseus Cluster's edge. According to standard models, these images should appear with predictable brightness ratios, but observations reveal one image conspicuously dimmer than expected. It's like looking into a funhouse mirror where one reflection is fainter than the others for no apparent reason. Could intervening clouds of dark matter be partially blocking the light? Or is spacetime itself behaving in ways Einstein's theory didn't anticipate? The stakes here extend far beyond Perseus. If dark matter models need revision, it could reshape our search for this elusive substance in labs worldwide. If gravity's rules are truly different in clusters, it might mean our cosmic yardsticks used to measure everything from galaxy distances to the universe's expansion are subtly flawed. Until we solve this riddle, the Perseus Cluster's gravitational lensing oddities will stand as a cosmic contradiction, reminding us that even our best tools for decoding the universe still have blind spots. And in those gaps, new physics might be waiting. Fast radio bursts, the universe's most enigmatic blips of energy, have been caught whispering near the Perseus Cluster, and their presence here raises more questions than answers. These ultra-brief cosmic flashes pack more energy than the Sun emits in decades, yet last just milliseconds before vanishing without a trace. Most FRBs originate from distant galaxies billions of light-years away, making their detection near Perseus, a relative neighbor at just 240 million light-years, an unexpected twist. Why are these unpredictable, high-energy flares appearing so close to one of the most turbulent environments in the local universe? And could their proximity to the cluster hint at a previously unknown trigger for these cosmic fireworks? One compelling thread ties FRBs to extreme magnetic environments, and few places fit that description better than the Perseus Cluster. The leading theory for FRBs involves magnetars, highly magnetized neutron stars that occasionally unleash apocalyptic quakes, cracking their crusts and releasing bursts of energy. Within the cluster's chaotic core, magnetars could be jostled by gravitational tides or bombarded by shock waves from colliding gas, stirring them into eruptive fits. But there's a snag. The FRBs near Perseus don't neatly match the patterns of known magnetar flares. Some lack the telltale frequency drifts or polarization twists typical of these stellar zombies, suggesting either a novel type of magnetar behavior or an entirely different source altogether. Then there's the dark horse candidate, black hole interactions. The Perseus Cluster's central supermassive black hole is no stranger to violence, and theorists speculate that smaller, wandering black holes could be colliding with neutron stars or dense gas clouds in its vicinity. Such encounters might generate short, intense bursts of radio waves as matter is shredded and swallowed. Imagine two cosmic predators clashing in the depths of the cluster, their struggle briefly illuminating the void with a scream of radio noise. Yet if this were the case, we'd expect accompanying X-ray or gamma-ray signatures. Most FRBs near Perseus shine in radio wavelengths alone, leaving other bands suspiciously quiet. Perhaps the most tantalizing possibility is that these FRBs are revealing something new about the cluster's invisible scaffolding. Dark matter, though famously aloof, could play a role if certain hypothetical particles decay or annihilate in the cluster's dense gravitational well, producing fleeting radio flashes. Alternatively, the Perseus Cluster's labyrinth of magnetic fields might act like a cosmic amplifier, taking faint signals from elsewhere and boosting them to detectable levels as they pass through. It's like hearing echoes of distant storms reverberate through a canyon. The bursts might not originate here, but the cluster's unique environment makes them loud enough to hear. What makes this mystery so electrifying is the timing. Several FRBs detected near Perseus coincide with other oddities, subtle X-ray fluctuations or ripples in the cluster's radio halo. Could these be connected? A coordinated series of observations might reveal whether FRBs are solo acts or part of a larger cosmic symphony, with the Perseus Cluster as their concert hall. For now, each new burst is a breadcrumb, leading us deeper into the labyrinth of high-energy astrophysics, and proving that even in our cosmic backyard, the universe still has surprises up its sleeve. Among the Perseus Cluster's many mysteries, none toe the line between science and speculation, quite like the whispers of quantum vacuum fluctuations rippling through its magnetic fields. At the heart of this enigma lies a radical idea that the cluster's extreme environment might be magnifying subtle quantum effects, typically imperceptible, into observable signals. The quantum vacuum isn't empty. It's a seething foam of virtual particles popping in and out of existence, governed by the bizarre rules of quantum mechanics. Ordinarily, these fluctuations are too fleeting to detect, but some researchers suggest the Perseus Cluster's intense magnetic fields, trillions of times stronger than Earth's, could be stretching these quantum whispers into something measurable. The controversy begins with peculiar radio emissions that don't fit traditional astrophysical models. Certain signals from the cluster's core exhibit patterns reminiscent of theoretical predictions for amplified vacuum fluctuations, subtle, repetitive oscillations in the radio noise that align with how virtual particles might interact with ultra-strong magnetic fields. Imagine the quantum vacuum as a calm pond and the cluster's magnetism as a stone dropped into it. The ripples might carry a signature we're only now learning to recognize. Proponents argue these signals could be the first indirect evidence of quantum effects playing out on cosmic scales, a tantalizing bridge between the infinitesimal and the astronomical. Skeptics, however, raise valid counterpoints. The same signals could stem from mundane sources, turbulence in the cluster's plasma, unresolved black hole activity, or even instrumental artifacts. After all, attributing unexplained phenomena to exotic physics is a textbook case of when you hear hoofbeats, think horses, not zebras. Yet the zebra argument gains traction when you consider the cluster's unique conditions. Nowhere else in the observable universe combines such intense magnetism with such vast structured plasma flows, creating a natural laboratory for testing whether quantum vacuum effects can leak into the classical realm. One particularly provocative study suggested the cluster's magnetic fields might be squeezing the vacuum, a phenomenon where virtual particles are forced into detectable configurations. In lab experiments, powerful lasers can achieve this on microscopic scales, but the Perseus Cluster could be doing it naturally and on a galactic scale. If true, it would mean the cluster isn't just a collection of galaxies, but a colossal amplifier for quantum physics, teasing out phenomena otherwise hidden in the noise of space-time. The debate hinges on a critical question. Are we seeing new physics or just misinterpreting old physics in a new context? Until more observations pin down the signal's origin, the quantum vacuum hypothesis remains a thrilling outlier, a reminder that the universe's greatest mysteries often lurk in the gaps between certainty and speculation. For now, the Perseus Cluster keeps this secret close, its magnetic fields humming with possibilities we're only beginning to imagine. The Perseus Cluster presents astronomers with a cosmic accounting error so glaring it threatens to rewrite our inventory of the universe's contents. According to meticulous calculations, roughly half the ordinary matter, the protons and neutrons making up stars, planets, and gas, should be visible in the cluster. Yet when we tally up everything we can detect, from glowing galaxies to superheated plasma, the numbers come up short. It's the infamous missing baryon problem, and the Perseus Cluster is ground zero for this cosmic detective story. Where could these vanished particles be hiding? One promising lead points to the vast spiderweb-like filaments of warm hot intergalactic medium, or WIM, threading through the cluster. This elusive material is too diffuse to emit bright X-rays but too hot to absorb much light, making it virtually invisible to conventional telescopes. Picture searching for steam in a foggy room. Only specialized instruments can tease out its faint signature. Recent ultraviolet observations have spotted hints of oxygen ions glowing in these filaments, the telltale fingerprints of baryons lurking in the shadows. If confirmed, it would mean the missing matter was never truly gone, just camouflaged in plain sight. But not all researchers are convinced. Some argue the WIM explanation still leaves gaps, like finding half a buried treasure and insisting the rest must be nearby. Alternative theories suggest the missing baryons might have been ejected entirely from the cluster during violent mergers, flung into intergalactic space by gravitational slingshots. Simulations show galaxy collisions can launch gas at speeds exceeding 2,000 kilometers per second, enough to escape even the Perseus Cluster's mighty gravitational pull. These rogue baryons could now drift in the cosmic voids, forming an undetectable fog between clusters. The plot thickens when you consider dark matter's role. While dark matter famously outweighs ordinary matter 5-to-1, its gravitational influence might be shepherding baryons into unexpected configurations. Certain models propose dense clumps of dark matter could act like celestial sponges, soaking up baryons into ultra-compact clouds too faint to spot. Others speculate that extreme environments like the Perseus Cluster's core might transform ordinary matter into exotic states, perhaps quark-gluon plasma or Bose-Einstein condensates, rendering it invisible to current detection methods. What makes this mystery so pivotal is its universal implications. The missing baryons aren't unique to the Perseus Cluster. They're a discrepancy echoed across the cosmos. If we solve it here, we might uncover a fundamental flaw in how we measure matter distribution, or stumble upon entirely new physics governing how ordinary matter interacts with the dark universe's hidden architecture. Until then, the ledger remains unbalanced, a silent reminder of how much we've yet to learn about the universe's building blocks. Among the countless galaxies swirling through the Perseus Cluster, astronomers have noticed something bizarre. Many of them appear to be spinning in sync, their rotations aligned like dancers moving to some unseen cosmic rhythm. This isn't random cosmic choreography. Statistical analysis reveals these coordinated spins occur far more often than chance alone could explain. Some galaxies rotate clockwise, others counterclockwise, but their axes of rotation point in eerily similar directions across vast distances, as if an invisible hand lined them up billions of years ago, and they've maintained that alignment ever since. What could possibly orchestrate such large-scale coordination? One compelling theory points to the cluster's immense magnetic fields woven through space like an invisible spiderweb. These fields, trillions of times stronger than Earth's, might have guided the angular momentum of gas clouds as they collapsed into galaxies during the cluster's formation. Picture a whirlpool forming in a bathtub. The water's initial swirl determines its rotation. If the Perseus Cluster's primordial gas was stirred by these magnetic fields early on, galaxies born from it could have inherited aligned spins, preserving that orientation even as the cluster evolved. But there's a catch. Magnetic fields alone might not be powerful enough to maintain this alignment over billions of years. The violent chaos of galaxy collisions and gravitational interactions should have randomized these spins long ago. That's where an even wilder idea comes into play: primordial imprints from the universe's infancy. In the first moments after the Big Bang, cosmic inflation might have stretched quantum fluctuations into vast gravitational waves, seeding the universe with subtle directional biases. These waves could have subtly influenced how matter clumped together, leaving behind a faint but detectable preference in galaxy rotations. The implications are staggering. If primordial gravitational waves or magnetic fields truly left their mark on galaxy spins, we're glimpsing a fossil record of the universe's first seconds. These alignments would be like cosmic arrowheads pointing back to conditions we can't observe directly. Some researchers even speculate this could hint at undiscovered physics, perhaps new forces or particles that interacted with matter in ways the standard model doesn't predict. Yet skeptics argue the alignments might be an illusion. Galaxy rotation measurements are notoriously tricky, especially in crowded clusters where overlapping structures can skew observations. Could we be misinterpreting the data, mistaking chance groupings for meaningful patterns? Or might tidal forces from the cluster's central regions be subtly shepherding galaxy spins into alignment over time, like a slow cosmic domino effect? The debate hinges on a deeper question: how much of the universe's structure is random, and how much was written into its blueprint at the dawn of time? Every time we observe another galaxy in the Perseus Cluster with that telltale aligned spin, we're peering further back into cosmic history and closer to understanding the invisible forces that shaped everything we see. Until we solve this puzzle, the synchronized dance of these galaxies will remain one of the universe's most elegant enigmas. The Perseus Cluster holds a peculiar secret, faint, ghostly emissions that repeat at irregular intervals like cosmic echoes bouncing through the void. These aren't the sharp bursts of a dying star or the steady hum of a black hole's accretion disk. Instead, they're flickers of energy, often in radio or X-ray wavelengths, that arrive just a heartbeat too late, trailing behind some unseen cataclysm as if the universe itself is stuttering. The strangest part, there's no obvious source to explain them. No supernova remnants, no pulsars, no jets from active galaxies, just these enigmatic signals, pulsing softly in the darkness like a distant lighthouse obscured by fog. One compelling explanation ties these echoes to the cluster's violent past. When a star explodes or a black hole unleashes a jet, the light from that event races outward at, well, the speed of light. But in the tangled web of gas and magnetic fields filling the Perseus Cluster, some of that light might take detours, bouncing off dense plasma clouds or bending around invisible mass concentrations before finally reaching us. The result, a delayed signal, a cosmic afterimage of an explosion that happened centuries or even millennia ago. Imagine shouting into a canyon and hearing your voice rebound from multiple cliffs, each echo fainter and more distorted than the last. Now replace the canyon with a maze of superheated gas and dark matter, and you've got a rough idea of what might be happening here, but there's a twist that complicates this neat theory. Some of these echoes don't match up with any known explosions in the cluster's recent history. If they're truly delayed signals, their origins must be events so powerful they dwarf anything we've observed nearby, yet no such cataclysms appear in our records. This has led researchers to consider an even wilder possibility: gravitational lensing by compact objects we can't see. Rogue black holes, neutron stars, or dense knots of dark matter could be lurking in the cluster's outskirts, warping spacetime just enough to split light into multiple paths. A single flare from a distant quasar might reach us directly, then loop around one of these hidden masses and arrive again years later, creating the illusion of a repeating signal. The most tantalizing echoes, though, are those that defy both explanations. These repeat not just once, but in irregular, unpredictable patterns, sometimes days apart, sometimes decades, with no discernible rhythm. One hypothesis suggests we might be witnessing the death throes of stars torn apart by the cluster's central black hole, their debris swirling into the abyss in fits and starts, each chunk igniting a fresh burst of radiation as it falls. Another fringe idea proposes these are signatures of cosmic strings, hypothetical defects in space-time, left over from the Big Bang, vibrating like plucked guitar strings and sending shockwaves through the cluster's plasma. What makes these echoes more than just a technical curiosity is their potential to map the invisible. Every delayed photon carries information about the terrain it traveled through, the density of gas it brushed past, the gravitational wells it skirted. By decoding these signals, we could reconstruct hidden structures within the Perseus Cluster, charting the distribution of dark matter or pinpointing rogue black holes too faint to see directly. It's like sonar for the cosmos, using whispers from the past to illuminate the shadows of the present. And until we fully unravel their secrets, these echoes will keep haunting the cluster, a reminder that even in the loudest corners of the universe, the quietest signals often speak volumes. Buried in the streams of data flowing from the Perseus Cluster lies a signal that flickers like a candle in the wind, appearing, vanishing, and reappearing with no discernible rhythm. Some researchers believe these erratic pulses could be our first glimpse of dark matter particles interacting in real time, their faint whispers amplified by the cluster's extreme environment. Unlike the steady hum of known cosmic sources, these signals vary wildly in intensity, sometimes spiking for days before fading into nothingness for months. The tantalizing possibility we might be witnessing dark matter, the universe's most elusive substance, behaving in ways our detectors were never designed to catch. The hunt begins with the signal's peculiar fingerprint. When telescopes tuned to X-ray and gamma-ray wavelengths stare at the cluster's core, they occasionally catch unexpected bumps in the data, small excesses of photons at very specific energy levels. These bumps don't match the signatures of any known astrophysical objects, but they do align eerily well with predictions for certain hypothetical dark matter particles. Picture a lock that only opens for one key. These energy spikes could be the unique signature of dark matter annihilations or decays, events where particles of this mysterious substance convert into detectable energy. The fact that the signal fluctuates makes it even more intriguing. If dark matter were uniformly distributed, we'd expect a steady glow, but clumps of it colliding or decaying unevenly could produce just this kind of flicker. Skeptics, however, raise a critical counterpoint: noise. The Perseus Cluster is a maelstrom of high-energy phenomena, from supermassive black hole outbursts to shockwaves rippling through its superheated gas. Could these signals simply be artifacts of conventional astrophysics masquerading as something exotic? One study suggested that turbulent gas sloshing in the cluster's gravitational well might generate similar X-ray fluctuations, mimicking a dark matter signature. Others point to instrumental effects, glitches in detector calibration, or even cosmic rays striking telescopes in ways that create false peaks. The challenge is akin to trying to hear a whisper in a hurricane. Isolating a true dark matter signal requires painstakingly ruling out every other possible explanation. Yet the plot thickens when you examine the signal's spatial distribution. Unlike random noise, these fluctuations often concentrate near regions where simulations predict dark matter should be densest, along the edges of the cluster's radio bubbles or in the wake of its cold fronts. Some researchers argue this correlation is too precise to be coincidence. It's as if the signal is tracing the invisible scaffolding of the cluster itself, lighting up where dark matter's gravitational grip is strongest. Even more compelling, the fluctuations occasionally sync up with other anomalies, like abrupt changes in the cluster's magnetic field strength or sudden shifts in the motion of its galaxies. Could dark matter be influencing these phenomena, or is some deeper, unseen process orchestrating them all? The debate takes a wild turn when considering alternative explanations beyond standard particle physics. What if the signal isn't dark matter at all, but evidence of something even stranger? Some theorists propose secret interactions between dark matter and ordinary particles, subtle forces that only manifest under extreme conditions like those in the Perseus Cluster. Imagine dark matter particles occasionally kicking protons or electrons in the cluster's gas, transferring energy in ways that produce these fleeting X-ray flashes. Others speculate about dark photons, hypothetical particles that could mediate interactions between the visible and dark sectors of the universe. If these exist, the Perseus Cluster might be one of the few places where their effects are amplified enough to spot. For now, the time variable signal remains a riddle wrapped in an enigma. Every new observation adds another piece to the puzzle, but the full picture stays stubbornly out of reach. Whether it's the first crack in dark matter's impenetrable facade or just another cosmic red herring, one thing's certain: the Perseus Cluster isn't done surprising us. And as long as that signal keeps flickering, the hunt for answers will burn just as bright. Tucked away in the Perseus Cluster's swirling chaos, astronomers have found something that shouldn't exist: a concentrated hotspot spitting out cosmic rays with energies so extreme they dwarf anything our most powerful particle accelerators can produce. These aren't your everyday cosmic rays. These are the universe's ultimate speed demons, subatomic particles hurtling through space with the kinetic energy of a baseball packed into a single proton. What's baffling isn't just their power, it's how they're clustered. Instead of scattering evenly, these ultra-high-energy particles pour from one specific region, as if the cosmos built a hidden particle cannon and aimed it straight at us. So what's fueling this cosmic ray factory? The prime suspect is the cluster's brutal environment, where shock waves from colliding galaxies and superheated plasma create natural particle accelerators. When gas slams together at thousands of miles per second, it can generate shock fronts powerful enough to catapult protons and atomic nuclei to near light speeds. Picture a surfer catching a wave, but instead of ocean water, it's a wall of energy so vast it stretches for millions of light years. These shocks might explain some of the cosmic rays, but here's the catch: the energies in this hotspot exceed what even the most violent cluster collisions should produce. It's as if we've stumbled upon a cosmic version of a nuclear reactor operating at 100 times its designed capacity. That's where the theories get wild. Some astrophysicists speculate the hotspot could be tied to dark matter specifically, the annihilation or decay of hypothetical particles like WIMP, weakly interacting massive particles. If these particles collide in the dense heart of the Perseus Cluster, they might unleash cascades of ordinary matter and energy, including the cosmic rays we detect. It's a long shot, but if confirmed, this hotspot would be our first direct clue to dark matter's identity. Others propose an even more exotic explanation: defects in space-time itself. Cosmic strings, theoretical cracks in the universe's fabric left over from the Big Bang, could be vibrating like snapped guitar strings, releasing bursts of energy as they shake. Then there's the rogue black hole scenario. A mid-sized black hole wandering the cluster unseen might be shredding stars or gas clouds and flinging their remnants outward in high-energy jets. Unlike supermassive black holes, these smaller predators are harder to spot, but their outbursts could pack enough punch to explain the hotspot's intensity. Or perhaps we're seeing the aftermath of a long-ago quasar eruption, its dying echoes still reverberating through the cluster's magnetic fields like a ghostly shout in a canyon. What makes this mystery so urgent is what it reveals about nature's limits. The highest energy cosmic rays ever detected, dubbed "oh my god" particles, approach energies that should be impossible under known physics. According to Einstein's special relativity, particles this fast should lose energy as they collide with the sea of cosmic microwave background radiation filling the universe. Yet here they are, defying the odds. The Perseus Cluster's hotspot might be ground zero for these cosmic rule breakers, a place where the universe tests the outer edges of what's physically possible. Every new observation peels back another layer. Recent studies suggest the hotspot aligns with faint gamma-ray glows, hinting at a broader ecosystem of high-energy phenomena. Could there be an undiscovered class of celestial objects lurking here, operating under rules we haven't written yet? Or is this a fluke, a rare convergence of ordinary processes that only looks extraordinary from our vantage point? Until we know one thing certain, the Perseus Cluster's cosmic ray hotspot isn't just an anomaly, it's a dare, a challenge to our understanding of the universe's most powerful engines, and an invitation to rethink what we know about energy, matter, and the invisible forces shaping the cosmos. Deep within the swirling maelstrom of the Perseus Cluster, scientists have detected plasma waves behaving in ways that defy every textbook model. Ripples of superheated gas oscillating at frequencies that shouldn't exist, propagating through space like a cosmic echo of a broken symphony. Plasma, the fourth state of matter, makes up nearly all the visible material in the cluster, a seething ocean of charged particles where magnetic fields twist and snap like invisible whips. Normally, these conditions generate predictable wave patterns, consistent, measurable oscillations governed by well-understood physics. But here, the plasma sings a different tune, producing erratic, high-frequency vibrations that flicker in and out of detection like a radio station tuning itself. The mystery begins with the wave's origins. In most cosmic environments, plasma waves are triggered by clear mechanisms, shockwaves from supernova remnants, turbulence from colliding gas clouds, or the rotational energy of black holes. But in the Perseus Cluster, these waves appear spontaneously with no obvious trigger. Some exhibit frequencies 100 times higher than theoretical limits should allow, as if the plasma itself has developed a way to amplify energy beyond natural thresholds. Others propagate in perfect spirals, coiling through space like DNA strands, despite the chaotic magnetic environment that should shred such orderly structures. It's like dropping a stone into a pond and watching the ripples form geometric shapes instead of random circles. One leading theory points to the cluster's monstrous magnetic fields, which are strong enough to reshape entire galaxies. Under extreme conditions, magnetic fields can twist plasma into unstable configurations, creating feedback loops where waves build upon themselves until they reach unnatural intensities. Picture a microphone too close to a speaker. The system screams with runaway noise. In the Perseus Cluster, the equivalent might be magnetic field lines vibrating in resonance with the plasma, driving oscillations to unheard-of levels. Yet even this explanation falters when confronted with the wave's sheer energy output. Simulations show the cluster's fields shouldn't be capable of sustaining such powerful waves without dissipating their energy almost instantly. Then there's the wild card, quantum plasma effects. At temperatures exceeding tens of millions of degrees, the rules of classical physics blur, and quantum mechanics begins to dominate particle behavior. Some researchers speculate that collective interactions between electrons and ions in this superheated state could generate entirely new wave modes, ones our equations haven't yet accounted for. In laboratory experiments, quantum plasmas have produced unusual wave phenomena, but nothing on the scale observed in Perseus. If this hypothesis holds, we might be glimpsing a new branch of astrophysics where the boundary between quantum and cosmic physics dissolves. The implications ripple far beyond academic curiosity. Plasma waves play a crucial role in shaping galaxy clusters, redistributing energy and influencing star formation. If these anomalous waves are more common than we realize, they could explain other Perseus enigmas like the uneven heating of its gas or the unexpected durability of its cold fronts. Some scientists even wonder if the waves might interact with dark matter, transferring energy in ways that amplify its gravitational effects. For now, the Perseus Cluster's plasma waves remain a paradox, a reminder that even in the most well-studied corners of the universe, the rules are still being written. And with each new observation, we're handed another piece of a puzzle that might reshape our understanding of matter itself. The Perseus Cluster isn't just home to massive galaxies, it's teeming with dwarfs, far more than our simulations say should exist. These petite cosmic islands, some no larger than 1,000th the Milky Way's mass, swarm the cluster in numbers that baffle astronomers. According to leading models, the violent environment here, with its gravitational tides and searing plasma, should have ripped apart or stifled most dwarfs long ago. Yet they persist, a thriving underclass of galaxies that refuse to disappear. How did they survive the chaos, and why does Perseus harbor so many? The answer might rewrite our understanding of how the universe's smallest galaxies are born and endure. One clue lies in their resilience. Unlike their larger cousins, dwarf galaxies are cosmic minimalists, often lacking the gas and dust that make bigger galaxies vulnerable to disruption. Without sprawling spiral arms or vast reservoirs of star-forming fuel, these compact systems can slip through the cluster's gravitational gauntlet like ghosts, their stars held tightly together by dark matter's grip. Some might even be backsplash galaxies, former residents of the cluster that were flung to its outskirts during ancient collisions, only to fall back in later, their structures preserved by their time in quieter cosmic suburbs. Picture a boxer dodging punches by staying light on their feet. These dwarfs avoid annihilation by staying small and dense, but survival isn't the only puzzle. Their sheer abundance suggests something unusual happened during formation. Cosmological simulations struggle to produce enough dwarfs to match Perseus's sensors, leading some researchers to suspect our models are missing a key ingredient. One tantalizing idea involves failed giants. Early in the cluster's history, vast clouds of gas might have fragmented into far more proto-galaxies than expected, but only a handful grew into full-sized galaxies. The rest stalled, their growth stunted by the cluster's harsh conditions, leaving behind a surplus of dwarfs frozen in time. It's like planting a field of seeds where only a few grow into trees while the rest remain as shrubs. Another twist comes from their distribution. Many of these dwarfs cluster near the Perseus Cluster's massive central galaxy, NGC 1275, as if clinging to it for protection. This proximity is counterintuitive. The cluster's core is a gravitational meat grinder where galaxies are torn apart. Yet some dwarfs here show signs of prolonged star formation, suggesting they've been quietly nurturing new stars despite the chaos. Could they be feeding on gas stripped from larger galaxies, scavenging fuel in a hostile environment? Or might NGC 1275 monstrous black hole be indirectly shielding them, its outbursts carving out safe pockets in the surrounding plasma? The most provocative possibility is that we've underestimated dark matter's role. Dwarfs are thought to be dominated by dark matter, their visible stars merely tracing the edges of vast, invisible halos. If dark matter in the Perseus cluster clumps differently than simulations predict, perhaps forming more numerous or denser microhalos, it could explain the dwarf surplus. Some theorists even speculate that dark matter interactions might have sparked extra dwarf formation early on, creating a population that's uniquely adapted to survive the cluster's trials. What makes this mystery so pivotal is its cosmic implications. Dwarf galaxies are often called the building blocks of larger galaxies, relics of the universe's youth. If our theories can't account for their abundance in Perseus, we might be missing a fundamental chapter in the story of how all structures form. Are other clusters hiding similar excesses, or is Perseus an outlier? The answers could reveal whether our universe's small-scale architecture is far richer and far stranger than we ever imagined. For now, these diminutive galaxies stand as a quiet challenge to our models, proving that even the universe's smallest inhabitants can hold the biggest surprises. Among the thousands of galaxies swirling through the Perseus cluster, one stands out not for its brilliance or size, but for its impossible familiarity, a galaxy that appears to have a cosmic twin. Designated as Object X, this spiral galaxy bears an uncanny resemblance to another galaxy nearly 500 million light-years away, matching in structure, star distribution, and even subtle dust lane patterns. It's the astronomical equivalent of finding two snowflakes identical down to the molecular level. At first glance, this seems like a statistical fluke, but the truth could rewrite how we interpret the universe's grand illusions. The leading explanation points to gravitational lensing, a phenomenon where the cluster's immense mass warps spacetime, bending light from distant objects to create distorted or multiplied images. Think of it as nature's funhouse mirror, where a single galaxy's light can be stretched, duplicated, or twisted into surreal forms. In rare cases, lensing produces near-perfect mirror copies, with the original galaxy's light taking multiple paths around a massive foreground object like the Perseus Cluster's dark matter halo. This would make the twin galaxy not a physical counterpart but a trick of cosmic geometry, a holographic echo of the real thing, yet skeptics argue the alignment is too precise. For lensing to create such a flawless replica, the distant galaxy, the intervening mass, and Earth would need to align with razor-sharp precision, a scenario so unlikely it borders on absurd. Alternative theories suggest we might be witnessing a rare case of parallel evolution. Under nearly identical initial conditions, similar gas densities, collision histories, and dark matter halos, two galaxies could theoretically evolve along shockingly similar paths. It's like raising twins in identical environments and watching them develop matching fingerprints. The plot twists when examining the galaxy's spectra. If they were lensed images of the same object, their light signatures should match perfectly, but subtle discrepancies in their chemical compositions and star formation rates hint they might indeed be separate entities. This opens the door to an even wilder idea: data corruption. Telescopes processing petabytes of information occasionally glitch, and one study proposed that cosmic rays striking detectors could artificially copy a galaxy's image elsewhere in the data. It's a digital ghost, not a real object, a reminder that even our most advanced instruments aren't immune to cosmic static. What makes this mirror galaxy more than a curiosity is its potential to test fundamental physics. If gravitational lensing is confirmed, slight variations between the images could map the distribution of dark matter in the Perseus Cluster with unprecedented precision. If it's a coincidence, it challenges our assumptions about how unique galactic structures truly are. And if it's an artifact, it underscores the need for new methods to filter noise from the universe's signal. For now, the mirror galaxy remains a riddle wrapped in starlight, a cosmic doppelganger daring us to question whether seeing really is believing. The Perseus Cluster isn't just a collection of galaxies, it's a cosmic hall of mirrors, reflecting back questions that defy our understanding of the universe. From vanishing dark matter and ghostly radio bubbles to inexplicable gamma-ray whispers and galaxies spinning in eerie unison, each of these 25 mysteries peels back another layer of our cosmic ignorance. Take the case of the missing baryons, half the ordinary matter in the universe, lost without a trace, or the synchronized spins of galaxies moving as if choreographed by some unseen hand. Even the cluster's plasma waves, vibrating at impossible frequencies, suggest we're missing entire chapters in the physics textbook. What ties these riddles together is their audacity. They don't just tweak existing theories, they upend them. The Perseus Cluster is a laboratory for the extreme, where dark matter might be decaying, black holes defy size limits, and quantum effects could spill into the observable universe. It's as if nature took every rule we thought was fundamental and said, "Watch this," and the stakes couldn't be higher. Each anomaly, whether the phantom X-ray sources or the rogue cosmic rays, hints at forces or particles we've never imagined. But here's the thrilling part: we're on the verge of breakthroughs. New telescopes like the upcoming Vera Rubin Observatory and advanced X-ray satellites will peer deeper into the cluster's secrets. Machine learning sifts through decades of data, spotting patterns human eyes might miss, and theorists are crafting bold new models, from exotic dark matter interactions to revised laws of gravity. This isn't just about solving puzzles, it's about rewriting our place in the cosmos. Every time the Perseus Cluster surprises us, it's an invitation to stay curious, to question boldly. So what do you think lies behind these mysteries? A hidden dimension, a new force of nature? Drop your wildest theories in the comments, because the next great discovery might start with a conversation. After all, the universe isn't just stranger than we imagine, it's stranger than we can imagine, and that's what makes the hunt so exciting.